Hi, everybody. Decided that we'd have class today at the Masai Mara Fields of Kenya, and I would be a giraffe. I would be a zebra for you. Hope you're doing well and coping with whatever is going on with you folks. I know there's still it's kind of a long slog having to deal with the quarantine, and it's more important than ever now, as you probably know. The rates are going up again, so be especially careful, please. Wear masks. My son's coming home this coming weekend, and because he'll be flying and coming from a large fraternity house where he's cohabitating with all these guys. We're going to have him quarantine when he gets home, which is going to be kind of a bummer until he gets tested, which we'll try to do right away. But we're looking forward to seeing him, even though he'll probably be locked in his room with a mask on for a few days. Anyway, I hope you're doing well. We should probably talk about a schedule for the next exam. And I got to let you know, I think it really does work out that the next exam makes most sense to be the week before Thanksgiving, or the days before Thanksgiving. But here's what I'm thinking of doing. So I'm thinking, okay, so it would be then, yeah. So next Friday, not tomorrow, but next Friday, the 20th and the 23rd, I want to make sure you have a review session in your sections. So I'm thinking of doing this, and let me know what you think. I would post the exam the evening of the 23rd, which would be after the Monday sections, and then have you finish it before, I guess we'll say midnight Tuesday. So I'd give you a full week, and you can take it any time during that week. Of course, it's the same type of test. It's 50 some questions, maybe a little less, and it would be 80 minutes for those 50 questions. I realize I'm going to have to do this around Thanksgiving, and I want to give you as much flexibility as possible. So, worst comes to worst, if you're going home or whatever, you can come back, or at least, have the weekend and then Monday after Thanksgiving to study, and then you could take it on Tuesday, which would be the 1st, I guess. Okay. The only problem with that is then your final exam is going to be pretty soon after that, but you're given that entire week. I'm thinking you'd take it between the 24th and 1st, which should give you a lot of flexibility. Okay, so we'll talk more about that as it comes up, but I think that's going to work best for the scheduling of the material and all that sort of stuff. So let me see if there's any questions. Make sure to do multiple tests. Sometimes it puts out a false negative if exposed only. Roy is talking about my son's COVID test. Absolutely. I thought you were talking about the next midterm, Roy. Yes, I completely agree, and that's why we're going to wait a few days after he comes home. Yeah, it's a very important point. Thank you very much for that. But any feelings about? I'm going to give you basically an entire week to do the test, and so I'm hoping that gives you enough flexibility. So yes, this is the second test before the final. There are 3 exams. They're all weighted the same, more or less, and they are not cumulative. But you need to have your second test, and that's probably going to work out best material-wise to be during that long week of Thanksgiving. Okay. All right. Okay. No other comments. We'll talk more about that next class, of course, but that's what you can plan on, which will give you a lot of flexibility. Erica likes that. Thank you, Erica. Okay, cool. Anything else you need to know? God, zebras are so cool, aren't they? They really, really are. And I guess supposedly the stripes are to kind of confuse predators. So they have trouble kind of singling out a specific zebra. Their visual cues are very dependent on kind of the contrast between light and dark, like a lion or a tiger or something like that. And the kind of crazy patterns you see on zebras makes it difficult for predators to kind of single one zebra out, because they see kind of just like a giant blob of stripes, which makes it harder to hunt these things, which is very cool. Okay, well, if there's no other questions, then I will de-zebra myself. Yes, I did know. Jason says that zebra stripes are like fingerprints. They are unique to a zebra. That is absolutely true. And I am very proud of my stripes, if I can say so myself. Okay, let me de-zebrify myself, and we will get into serious science. There I am. Okay, so we are talking about plasticity. We're talking about touch, but we're really going to use touch to understand plasticity. So let's go back to the last slide we were discussing, which was on touch and plasticity. And just to remind you of what we were talking about, we kind of started discussion of plasticity and touch in the context of cross-sensory plasticity. We're going to branch out with that this time, but it's kind of a very kind of nice way to get into the whole issue of plasticity, because we have some intuitions about that already, from discussions of Daniel Kish and Brian Bushway and other folks that have had some sort of sensory loss, that their other senses kind of take over, and that taking over involves kind of a shifting around of the responsibility of the brain. Right, so we do know that the visual cortex, let me put on my brain hat here, the visual cortex, it's called the occipital lobe sometimes, back here is usually responsible for vision, right back there, but if it doesn't get vision, then it is available to help out with the other senses. So where the strip on the side of the brain called the sensory strip here does help everybody with vision. Hopefully you're seeing that it's not backward. It looks backwards to me, but hopefully it doesn't look backwards to you, but you get the idea. That's when we all touch things, whether we're sighted or not, we do light up that part of the brain. But if in fact we have lost our sight or we have been blindfolded for some period of time, now you know, we do make use of the visual brain too. And remember that the visual brain is going to kind of become active, even if it doesn't necessarily have a lot of experience with touch after the blindfolding occurs. Right? And we talked a little bit about that when we were discussing the fact that that's going to happen if you're blindfolded for 5 days, but you're not really training anything like Braille or anything like that. Which reminds me, I almost forgot this, I promised to give you some extra questions today. So let me do that right now. I'm going to give you 2 polling questions while I'm still thinking about it. Because I forgot to last time, forgot to set them up last time. Okay. Good. We just talked about this. And I will read the question for you. By the way, I'm hearing somebody's microphone is on, so if you don't mind turning that off, that would be wonderful. Okay, here's the question. After 5 days, which of these subject groups would be best able to discriminate raised dot patterns by touch? A group given 6 hours of Braille training each of the 5 days. B, a group blindfolded and given 6 hours of Braille training each of the 5 days. C, a group just blindfolded for 5 days without the Braille training. Or D, the groups described in B and C would be equally good at discriminating dot patterns. If you want to take a quick look at that previous slide, that's fine, but the most important thing is that you get this question in, you take a picture of it, you get it in your notes, so you'll be ready for the exam. So if you don't get it right, no problem, it's all anonymous anyway. Ooh, there you go. I'm going to take off my brain hat while you guys are working on that. It is a little tricky, but if you'll think back to the previous slide, I think you'll understand this. Because it really captures, this question captures a very surprising result. Oh boy. I'll give you another 10 seconds. Great. Let me end the poll and share the results. You know something? Yeah. I don't know if you're having this problem, but I cannot see how many people. Oh, I can see the percentage. I can't see this line down here. Usually there's a red line that indicates the most popular response, and I can't see it. Maybe you can from your end. But the important thing is this is the most popular response. 57% of you answered D or 4 or whatever it is, and that is the correct answer. The correct answer is the groups described in B and C would probably be equally good at discriminating dot patterns, which is really interesting because it suggests that it's important that you're blindfolded to actually involve the visual cortex in helping out. Okay, if it's certainly being blindfolded and learning Braille is going to help, but you don't even really need to be touching. Once the visual cortex is involved, and it will be involved if you're blindfolded and doing nothing for 5 days, then it's going to help you touch. Okay, so the correct answer for this question would be D. All right, I'm going to do one more and then we'll continue with our lecture and ask more questions later. Okay, let's do another one. All right, this one has to do with Braille. What is the main reason that most blind individuals have better touch sensitivity? A, most blind individuals use Braille. B, their touch brains can be reassigned to vision. C, their visual brains can be reassigned to touch. Or D, both A and B. Okay, think about this one. Remember, we learned some stuff. We learned something kind of maybe a little disappointing about Braille in the last class. So think about the answer carefully. I'll go ahead and do this one and I'll give you 30 seconds for it because we should move on. Good. You're thinking hard. That's great. Okay, terrific. Again, as long as you get the question in your notes, that's what really counts here for you. And you learn the answer, of course. Let me end it and share the results. And now I'm seeing the red, I think it's red line. The correct answer is, in fact, C. I think most of you, in fact, remembered that most blind people actually do not use Braille, which is, I think, very surprising to folks that first hear that. Certainly was surprising to me. It's only 10%, and it's probably less than 10% now. Now, it is not that the touch brain can be assigned to vision. It is, in fact, the opposite. Because their visual brain no longer gets any input, it can be reassigned to help with touch and hearing, but now we're talking about touch. So the correct answer is C, and most of you got that. So the answer D is incorrect because most people don't read Braille that are blind, and it's not the touch brain reassigned to vision, it's the visual brain reassigned to touch. Okay, terrific. Let me just see if there's any quick questions on either of those from your chat, and then we'll. You're going to get 2 more questions, Marvin, later on. Yeah, these are questions from the last lecture that I forgot to post last lecture, so I wanted to be fair. Okay, and hold on just a second. Okay, Alexa asked a great question. How can you know Braille if you haven't learned it? So actually, they are not, oh boy. I'm having a little problem with the connection. I keep losing the chat, but let me see if I can bring it. Oh, wait, maybe if I get rid of this. Okay, there it is. Oh, shoot. Okay, Alexa asked a good question. Based on the first question, it would seem that they know Braille at the end. No, but these are people that are just blindfolded for 5 days. They're learning something like Braille. It's really just dot discrimination, but it isn't really Braille. Okay, so I kind of used Braille as kind of an example, and in fact, in that study, they use raised dots, but the raised dots in that study never really formed Braille letters. Okay, so that's the answer to that. I think you've cut out. I'm froze. Did you freeze? Oh boy. Am I okay now? Please let me know if I'm okay now. I saw yeah, okay, I'm back. Good.
Yeah, it's better now.
Thank you very much. Yeah, It's pretty warm here on the African veldt here. I'm surprised I froze. Okay, I'll keep my eye out. I get a little notice if it cuts out, so hopefully it will work fine. Okay, so good. That's great. We'll ask more questions later on. You did very well on those, though. We finally ended up talking about that there are some instances of everyday touch, like when we're putting our hands in our pockets and feeling a key, that we actually do activate our visual cortex, even though we're not visually impaired. And that is supported by fMRI evidence. You know, you have people kind of reach into a bag or something in the scanner, and you ask them to pull out something, and they, you know, kind of take their time and try to feel for things and then pull them out, whether it's something like a key. And you'll see that there is activity back in the visual cortex. Or once you establish that, you can then use our wonderful device, this transcranial magnetic stimulation device, and break temporarily the back of the brain here where the visual cortex is, and find that people are in fact a little inhibited, a little less accurate at pulling something out of a bag that they can't see, like pulling keys out of a pocket. Okay, and we left off with this point, cross-sensory plasticity, which we've been discussing through last lecture and now this one, is not just something you see in the blind. It is something you see for all brains. And you can induce it even, you know, in very, very subtle visual deprivation sort of examples. Yes, certainly the 5-day one is not subtle, but 3 hours of visual deprivation, and you see the visual brain helping out with touch. And then even reaching into your pocket, not being able to see what you're touching, that brings about a little bit of involvement of the visual cortex, the visual part of the brain back here, in helping us touch. Now, I'm going to talk about one more aspect, I think, of cross-modal plasticity I think you'll find very interesting. And it has to do with devices that have been designed to help the blind be able to navigate scenes or be able to navigate environments using a really unique sort of device. So let me talk a little bit about the history of this, because I remember learning about it when I was a kid going to my dad's office. I think I might have mentioned to you, it's in the book as well, that my dad was the director of an agency for the blind and had these really cool devices, including something like this. So they were kind of trying to consider how you could get a blind individual to basically get information about a scene, a cluttered scene like, you know, in Africa, and whether touch could be used for that purpose. So back then, and we're talking about the 60s and 70s, they had this device that would kind of fit on the back of a blind individual that had little posts in it. You can kind of imagine an array of little metal posts. I think there were probably about 50 posts, and they would just lightly touch a person's back. And it was connected to a camera that could be held. The cameras back then, a video camera, they were really pretty big. It wasn't a very transportable sort of device. But what they could do is kind of move it around, and the camera would translate the images in front of it to little vibrations on the posts that were touching a person's back. So the visual information would get transmitted to the vibrations of the posts on the person's back, and in theory, that person would then be able to get a sense of what was going on out in front of them, right? So they'd get a sense of whatever other people could see by, I guess, a kind of, I don't know, an array of how they were being touched on the back. Did it work? Well, it took a lot of training, but it worked okay. I mean, you know, people really couldn't truly navigate very well with it, but they could make things out in a room like, oh, there's something like a table there, there's something like a chair or a bookcase, kind of. And it took a lot of training. And it was huge and bulky and took a lot of electricity. To get these things to vibrate took a lot of electricity. More recently, they've taken that same principle and have learned to make it much more technically feasible by using something called a tongue display unit. And that's what you're seeing right there. That's what this is showing here. So basically, this is a mini version of that grid of posts that you put on people's backs. Now what you're doing is you're putting it on people's tongues. And the reason you do this is because, first of all, the tongue is a very sensitive place. It's much more sensitive than the back when it comes to touch stimulation. But it also requires less electricity. So potentially it could run off of like a battery that powers a laptop computer or something like that. And these are not vibrating posts here. Instead, they're little electrodes that kind of provide a very subtle little electrical charge that then basically charges the tongue, actually connects to the tongue. Now, it sounds like it'd be like a torture chamber sort of thing, and it's not. I've experienced it. And kind of what it feels like, you know what it feels like? It kind of feels like having fizzy water on your tongue. Yeah, I can kind of feel the fizzy water on my tongue, and I could feel the fizzy kind of continue as it went back my tongue, back to the back of my tongue. And it feels like that, or imagine champagne bubbles, where the bubbles are kind of really distinct if you've had champagne. That's what it feels like. And the idea here, though, is that you could take an image from a camera, a video camera, that could get translated to the electrical currents that are coming out that little grid of electrodes there, and kind of basically, provide a touch image to the tongue. If, for example, a person's looking out and there's a ball, then the stimulation here on the tongue would be circular, and a person could learn to, I guess, read this tongue stimulation after some practice and know what's out in the world. It's much more portable. I mean, I've played with this thing. It's not much bigger than, I don't know, it's bigger than a phone. It's like a kind of a couple of iPhones put together. And of course, you do have this strip that goes to your tongue, but it's so much more manageable than the old systems. And what I have here, oh shoot, let me make sure I've got the sound ready to go. I have a little video that shows this, and it's kind of cool. I think you'll find it interesting. Hopefully it will look okay. Again, I know the video isn't perfect in terms of its image, but hopefully you'll hear enough of it and see the image to get a sense of what it's about. It's pretty cool.
At first glance, Roger Bain looks like an independent guy who loves his power tools. And he is. But here's what he's actually seen since he was a young man. But part of his world is slowly coming back into focus through experimental technology called BrainPort. One day it could actually help blind people see, in a sense, using their tongues. Yes, their tongues. It swaps tiny cameras for eyes and transforms the images into electrical impulses that are felt on the tongue.
It's as if it's drawing on the tongue the still image, and so if you capture the images fast enough, paint them fast enough, it's like a video display. Instead of being on a screen, now it's on your tongue.
You know, when you're a kid, I don't know if you did or not, but when you're kids would draw on your back and you try to guess what it is.
In normal vision, the eyes send signals to the middle of the brain. From there, the signals are sent directly to the visual cortex at the back of the brain. Not so for the blind. The BrainPort retrains the way the brain processes information by first stimulating the tongue with an array of tiny electrodes. The nerves in the tongue send signals through a different pathway to the brainstem and the area that deals with touch. Eventually, the blind person learns to interpret touch as sight in the visual cortex. Sounds impossible? Well, watch how Roger walks through the BrainPort office without any guidance. He can navigate this obstacle course, picking out specific shapes.
Excellent.
The camera sees this image, Roger feels it on his tongue, and that's how he can even spot the logo on a football jersey.
Very good.
Other blind volunteers recognize numbers.
9.
It's like learning a language. At first, you might need to spend a lot of time thinking about what the translation is. I may feel stimulation in the right front part of my tongue. What does that mean? But very rapidly, like learning a language, you might learn a few quick vocabulary, and eventually you become so fluent that you don't need to think about it anymore.
Blindfolded, I try it myself. After a humbling first attempt,
I want to say it's diagonal.
Okay. And this one is vertical.
I managed to understand some of the BrainPort language.
I want to say it goes this way.
You are correct.
Okay.
The technology is improving. Today, a car looks like this to a Brainport user. A few months from now, they hope it will look like this. And in a year and a half, more like this. For the blind, they're a glimpse at more freedom.
This develops where the next generation can really get benefits from it. Even if I don't get the greatest out of it, I'm still can determine if I can see their eyes and maybe even see a smile or a grin, you know, that kind of stuff. It can be cool.
And for the rest of us, it's a miraculous look at how our brains can be trained to rewire themselves. Daniel Seberg, CBS News, Madison, Wisconsin.
Okay. Yeah, it's pretty cool. I mean, in theory, it's very cool, and I think that it does teach us a lot as a kind of a scientific experiment about plasticity and that sort of thing. Is it practical? Is it usable? Well, that's another story. You can buy this if you're interested, and it is, you know, I think the blind can get access to these. They're very expensive, but you know, often there are grants that help blind individuals acquire them. But very few blind people use them. I think there are some natural limitations to this that's going to make it difficult. And you know, other technologies have come up. You know, things have actually occurred with transplantation and you know, direct visual stimulation either on the brain or in the back of the eye that are probably going to be more promising than this. But it is, I still think, a very, very interesting sort of phenomenon. So how does it work? Okay, so how well does it work? Well, without training, like you saw that reporter there, in fact, you can recognize things like lines and curves and that sort of thing. With, say, I don't know, maybe a week or two of training, you'll start to be able to see other things like shapes, and then you start noticing things that move, like a rolling ball. But it still takes many, many months to get to those other sorts of things listed there. To be able to traverse a maze, they set mazes up in the laboratory and asked the blind individuals to try to traverse it, and it's still very difficult. That individual you saw, I can't remember his name now, but he does not, he as far as I know, he still does not use it as his main means of navigation. But you know, it's effective to the point where he can do the demonstrations you saw. It does take a long time to recognize letters. It's not going to, I can't imagine it would ever actually be used for reading or anything like that. There's just too many other technologies that support that sort of thing. But here's some interesting stuff that goes on. As they mentioned, at first it is like translating. It is kind of like you feel a pattern of tickle and you kind of have to start associating a specific pattern of kind of bubbly tickle on your tongue with, you know, things that you're then told you're looking at, right? So it does take some kind of feedback. Someone has to be there and say, that's, you know, that's not a vertical line, that's a horizontal line, that sort of thing. And you have to kind of do that over and over again. So it's, you know, it's kind of like learning a new language, as she said, learning a new kind of script or something like that. But then after a while, it does become a little bit more like second nature. Not necessarily with letters, but, you know, when you're able to traverse a maze, interesting things start happening. And yes, you still do feel the tickle on your tongue. And I'm sure this gentleman, who's probably one of the better folks to ever use it, would say that, yeah, I can, if I focus on it, I can feel the tickles on my tongue. But he's no longer having to go through that translation. What he starts to experience is things out in the world. You know, he starts to experience, there's a, you know, one of the walls of the maze in the laboratory is there. There's a table there, there's a jacket there, that sort of thing. And when he experienced things outside of his kind of own body, right? So when you're feeling the tickles, that's kind of part of your body still. But when you start experiencing things outside, interesting things happen. Because it's at that point, it seems, that the visual cortex comes into play. And I always thought this is one of the most interesting kind of connections between what's perceived and what is going on in the brain. There's seems to be some sort of correlation where when you begin to perceive things out in the world rather than just in your tongue, that's when the visual brain really, really gets involved. Remember Daniel Kish, I think we talked about this with regard to Daniel Kish. It's not like he's, using echolocation and really ever hearing, differences in sound. Maybe he can introspect a little bit, but most blind people didn't even know it was sound, right? Remember facial vision. But what he does perceive are things out in the world. Here's a wall, here's a tree, a lamppost, a basketball court pole, or something like that. And his visual cortex is involved all that time. And so I've always found that to be a really interesting correlation. You perceive, using this device, using echolocation, you perceive the things out in the world, that real things exist out in the world when the visual cortex is involved. Before that, no, it still feels like something on the tongue. It's probably, just that little strip on the tongue that we call here the sensory cortex, that little strip. But then once the visual brain gets involved, all of a sudden, objects seem like they are out in the world, not just tickles on your tongue, which I've always found very interesting. So what's the resolution like? Well, when they made that video, I think they said the resolution was this. I believe they've gotten it to where it's like this. And really what they've done is just add more little diodes and made this a little bigger. But I always think there's going to be kind of a constraint on how much resolution they can give, because the tongue is very sensitive to touch. It's much more sensitive to the back, as I said before. But is it sensitive enough that you're going to be able to feel whether 1 or 2 dots is being stimulated and that sort of thing? It's not clear that that's going to be possible. So I would say the resolution is probably still too poor to be used. I don't think it's really an issue of what the technology how the technology can prove. Rather, it's an issue of how much touch sensitivity your tongue can actually have, which I think is an interesting aspect, even if it's a little frustrating for the folks that want to design and have people use this sort of device. Let me take a quick stop here to see if there's any questions, and then we'll go on. Okay, is this how Helen Keller navigated? No, you're going to learn about Helen Keller tomorrow or Monday, whenever your section is, and you're going to see this is long before she was. She was alive long before this was produced. In fact, long before the devices for the back were produced. I can't remember when she died, but she died. I don't think she ever really used any aids for the blind besides a cane and a dog. But she learned, as you'll see, to compensate for things really impressively using other sorts of skills. Was this a few? Yeah, so the video, I think, is from 2011 or 2012, I think. But I have talked to the people that work on these sort of things since, and I talked to a lot of friends that are kind of very active in the National Federation of the Blind. And I don't think many blind people really use these things. I don't think anyone uses it regularly for their primary means of navigation. So is this really taste? Roy asked. That's a really good question. Well, yeah, in a sense it is, because now that taste involves touch. Touch is a really important part of taste. But it doesn't really, it's not like when it's on your tongue, well, when you first put it on your tongue, it does taste pretty terrible. But, you get used to that taste. But it's not like when they turn these things on that the taste changes. It's not like that. It feels like a tickle, so it's like, again, think about fizzy water on your tongue or something like that. It really is more of a tactile experience. And you do find that that sensory strip on the brain is the thing that's lighting up. But you're right. Yeah. It's the tongue. And we know that, touch certainly influences our experience of flavor. So yeah, maybe indirectly it is. Good question. Okay, we will come back to this, but we'll not come back to this exactly, but we'll come back to this issue of cross-modal or cross-sensory plasticity quite soon. But before we do, we need to get into some kind of more technical aspects of the course. So this slide, not so much, but the next slide is going to be one of the more technical slides of the class. I'm giving you forewarning so you can, I don't know, what do you like to do when you have to really concentrate hard? Get out your fidget spinners. Everyone get out your fidget spinners. All right, whatever it's going to take. This is going to be complicated, not here so much, but in the next slide. Okay, let's see. we're going to be talking just about how our experience of touch changes the brain, and changes specifically the part of the brain that is responsible for touch. So that is what you are seeing there on the top right. You are seeing a piece of the brain right here, and it's a piece of the brain we've already discussed. You are seeing the strip here, but now you're seeing it like from the front. So if I were to take that image there, that kind of weird looking image there, and turn it to the side, it would look like this. And now you're looking. And what's that going to allow you to do? Well, it's going to allow you to see how different parts of the body are represented along this strip. So it's pretty cool, right? It's like the body is mapped to the sensory cortex, or sometimes it's called the somatosensory cortex. You don't have to worry about that. But it's a mapping. And it's an interesting mapping, right? Because if you look at that mapping, it's not really based on how large a body part is, right? Certainly, we would, what is that? Yeah, here's our legs right here. Our legs are much bigger in size than our lips and face are. But look how much of the little map there is dedicated to the face and lips, and even to the hand. I mean, the hand more is dedicated to the hand than most of the lower leg, even though our hands are relatively small. And what in the tongue, my gosh, look at all this. So what does that mean? Well, it means that the amount of space that's dedicated to a body part depends really on the function of the body part. We need our face to be very sensitive to touch. We need our lips to be very sensitive to touch, for purposes of speaking and purposes of eating. We need our hands to be very sensitive to touch. We don't need a lot of sensitivity on our thighs. Yeah, of course, when someone touches, tickles your leg or something like that, you can feel it. But the sensitivity on your leg is nowhere near what it is on the face. And I think that's probably pretty intuitive to most people. Okay, so that's what your brain will look like before any sort of kind of long-term touch experience. But what I'm going to suggest is that when we start getting experience touching something, maybe based on a hobby we have, based on a profession that we have, where maybe we use tools a lot in our hobbies or professions, things start shifting around. And this isn't just an issue, this isn't just true of blind individuals, this is everybody's brain. That this map along the sensory strip here is going to shift depending on our touch experience. And that's what we're saying here, that there's plasticity in the touch brain area. So again, we're talking about this strip, we're just looking at it from the front here. Okay, let's go first talk about Braille users, because clearly that's a really good example of touch. And you remember what Braille looks like. Pretend I have a page of Braille right here, and it's going to have raised dots on it. Okay, I actually do have a Braille book somewhere. I should have brought it in. Anyway, the way the blind use Braille, the few that do, is they use their three middle fingers to kind of scan like this a Braille page. Okay, that's how they're taught. Actually, they use both. If you were, from the perspective of the page, if you were at the page, you'd be looking at my fingers and I'd be doing this. Okay, which is interesting because it really emphasizes the touch kind of skills of these three fingers. And what you find is, after somebody learns Braille, using those three fingers of both hands, that this map actually changes. So you can actually see this, if you were to kind of zoom in on here, you'd see what parts of this little crevice down here of the brain was dedicated to the different fingers. And it would be for, many people, fairly even between the fingers. But for the blind who do use Braille and have to, touch things very precisely with these three middle fingers, what you find is that they have a larger area here dedicated to the three fingers. So this plasticity occurs just at the level of the touch brain area, right? And folks that are learning Braille, absolutely, their areas kind of shift around a little bit, and it takes a little while, of course, but it shifts around a little bit, and now those areas are given, there's more proportional area is given to those three fingers on each hand than the thumb and the pinky. Okay, which is really interesting. But you don't even have to be a Braille user. I mean, that maybe is one of the extremes where you're using, Braille users at least used to use these fingers all day long, okay? Don't know what it's like now, but certainly back when this research was conducted, it was like that. But you don't have to be a Braille user to show these sorts of effects. Maybe some of you are violinists or violists or, guitarists, right? What you find is if you, in fact, are a violinist, here, I'll get out my violin. Okay, so it's not a violin, but it kind of looks like a violin, kind of. And here's my bow, all right? Can I make sound with it? Hey, it kind of makes sound. That's kind of cool. Anyway, pretend this is a violin and this is a bow. Okay, if I'm taking violin seriously, or if I'm a guitarist and I'm learning something on the fingerboard here, what happens is I'm using the precision of my fingers on my left hand more than the precision of the fingers on my right hand. Yes, my right hand is used to grip the bow, okay, but it's kind of a very kind of simple, general grip. These fingers have to be very specific and very precise. So if you look at violinists or guitarists or cellists that have played for many, many years, what you find is, right-handed, of course, we're talking about, like I just showed you, that the fingers on their left hand have more area dedicated to them on the sensory strip here than the fingers on the right hand. Okay, violin players have more area dedicated to the left-hand fingers than the right. And that's because they have to have such precision, and they have to have, they have to use touch, kind of as feedback to know how hard to push and all that sort of thing. And that is absolutely the case with right-handed violinists. Here you're seeing how it's dedicated to the finger. And in this case, it is, it's just so you probably know this from other courses, but it's not important that you know the details, but the left side of my body maps to the right side of my brain, which means that this cortex here, this part of the brain, this sensory strip here, is going to detect what my left hand fingers are doing. This part is going to detect what my right hand fingers are doing. And because I have to be so precise with my left hand movements, the area of this map is going to reform and dedicate more to those fingers, okay, than my right hand will have to do, than the right part of the way the right part of the body is mapped onto the brain. Okay, so that's really what the important part of what you need to know. Not just true of violin players and guitarists and all that stuff. It's also true of anybody who uses any tool. Okay, so here's an experiment. Actually, yeah, this shows it down here where they just over the course of I think it's an hour or maybe a 2-hour experiment, they have people kind of learn to use and become semi-experts at manipulating tongs to move corks around a board. Here, there's tongs, right? I just got it on my barbecue. This is one of the few things that's good about teaching remotely, right? I have all these props. This is from my barbecue, but I washed it. Anyway, for that experiment, what they had people do is kind of use tongs to manipulate corks around a board, a wooden board that had holes in them, right? And say, I think it maybe was an hour, maybe 2 hours. What they found was, again, a shifting of the strip here. And it was if the hand, okay, was given a little bit less area, and then there was almost an area here that didn't seem like it was really dedicated to anything at all. And here's the thing we were talking about the other day. It seems like if you use a tool long enough, including a screwdriver or hammer, I mean, this is something you use regularly, okay, what you're going to find is that the brain's going to shift around almost to make room for the tool you're using. In this case, it's tongs, and it's been, these sort of experiments have been done with carpenters and people who use the same type of tool over and over again. And you've heard that, yeah, for a constant tool use, the tool becomes an extension of your body in some way. Here's an example where it not only becomes an extension of your body, but it becomes part of your brain and how your brain is representing these tools that are now have been added to your appendages, more or less. Okay. And then finally, one example I wanted to talk about was how touch is enhanced. Okay. So this actually, this is a brain experiment too, but now we have a way of measuring the outcome of this brain experiment. So you take pianists, okay, people who play piano, for a hobby for a good portion of their lives, okay, and you test their 2-point sensitivity. We talked about this before. In fact, that's that little device I was mentioning. Again, this would be the sort of thing that would be used to determine, as somebody gets older, how much difference do they need, how much space do they need between, okay, this is the best I could do for this one. How much space do they need between 2 points to feel that it is 2 points, not 1 point? So if I have these 2 points, is this showing up? It's not bad. Yeah. See this? 2 points? If I have these 2 points right together on my hand, it's hard to see this. I might not be able to tell it's 2 points, but so I'll have to pull them apart until I am certain they're 2 points. And what you find is that someone like a pianist who has all this touch experience, this fine touch experience from pressing down on the keys and getting the feedback from that touch, okay, they will have more sensitivity in their fingers when it comes to this kind of 2-point test, which I think makes perfect sense, right? So yes, the brain shifts around as the more we touch, the brain shifts around. And one of the outcomes of that kind of shifting map is to allow a person to have more sensitivity to what they're touching, which is really important for musicians and people who use tools regularly and for Braille users. But certainly you probably have something that, if you have a hobby like a sport or something like that, or you play an instrument, or you're a cook that regularly uses a certain tool or something like that, your brain has shifted to kind of accommodate that as well. Okay, let's take a quick break here and see what the questions are, and then we will we'll do a polling question. Yes. Mustafa asked a great question. Does the brain make room for that tool only on a specific hand? Or yes. So, tool users will typically use their right hand for part of the tool. There certainly are tools that are going to take the involvement of both tools, but I'm a right-hander, so when I use a screwdriver, I'm going to pretty much use my right hand. Now, if I were somebody who used a screwdriver every day for a long period of time, certainly it would be just that part of my brain, the one dedicated to my right hand, that would kind of make room for that screwdriver on the map. It's a great question. Yes, so it would be hand specific. How would modern humans touch center would have changed from our ancestors? That's a great question, Roya, because I think our ancestors, you're talking about our ancestors, coming up from the fields and the woods and all that sort of stuff, they touched very different things than we touch. I mean, I could imagine that your touch map as somebody that grew up in the 2000s is very different from my touch map, just by virtue of that I used a pencil and pen all my life until computers came around. And I know you folks are taught to use pencils and pens, but boy, I doubt you use them very much. I know my kids certainly don't. And that's a tool. A pen and a pencil is a tool, a different tool from a computer keyboard. So yeah, that map's going to be very different just in the span of less than maybe a few decades or something like that. Let's see, Casey asks, is this related to being left-handed dominant or right-handed dominant? Yes, in a way. There's other things of the brain that kind of are more kind of firmly established that make people left or right-handed. As I understand it, I'm not really an expert at this. I think that is something that's considered to occur in utero. But yes, then it is likely that the way the maps form for the two hands, for the touch maps, is going to be different because a left-handed person will use their left hand for tools. And that kind of feeds back and maybe makes somebody even, more of a left-hander, more of a right-hander as they develop. I think that's probably the case. It's a very, very good question, Casey. Okay, great. Let's do a quick polling question, and then we'll do the hardest slide of the class. But don't worry, I'm going to try to explain it really simply. All right. Okay, this is going to be so easy. It's right there on the slide. No problem. Has to do with violinists. So I read it first. If you're an expert right-handed violinist, chances are your touch brain, A, has disproportionately less of its area dedicated to your left-hand fingerboard fingers. B, has disproportionately more of its area dedicated to your left-hand fingerboard fingers. C, has the same amount of brain area dedicated to the fingers as an expert Braille user. That's not a great answer. I'm going to change that probably. Well, I'll leave it in there for now, but I'll talk about it when we answer it. Or D, has the same amount of brain area dedicated to the fingers as non-experts. Yeah, that C question, the C answer is not great. I'll tell you why in a second, but it's not the right answer. Okay, so go ahead and do it. No, C, that's not the right answer, so you can ignore that one. Someone chose C just to confound me, I think. I'll give you 10 more seconds and then I'll explain this. Okay. Most of you got it right. The correct answer is B. Let me say why it's not A. Because it's for right-handed violinists, and just assume we're talking about right-handers through most of this. It is, in fact, the case that their left hand is on the fingerboard, and I specify that in the answer anyway. This is the precision touching that needs to be done with the left hand. Okay, that's the precision touching. For that reason, it's going to be B, you have disproportionately more brain area dedicated to those left-handed fingers, not the right-handed fingers. I'm sorry, I didn't say right. Has proportionally less of its area dedicated to your left hand. No, it's not less, it's more, which is B. And D, I'll get back to C in a second, D has the same amount of dedicated to fingers as non-experts. No, the expertise allows you to change your brain, and that's going to be true of expert violiners. Even, when we're talking about experts, we're talking about people who've done it for a long time, even as a hobby. Okay, so if you've been playing an instrument for a while, if you've been playing a sport for a while, all that stuff is going to show brain differences. Okay. The C thing, I think, is a bad answer. The C answer is a bad answer because I understand what we were going for there, because what happens with the Braille person is they're going to have not just more area for the left-hand fingers, but more area for the right-hand fingers too, because Braille involves both hands. It's just, it's a little distracting. So yeah, I'm not sure what to put in there. I'm not going to change the question. I don't want to do that to you folks. But just remember it's not C, and remember why it's not C, because for the Braille user, they use both hands. Okay, and so it would be, equal amount on both sides of the brain. But that's not what we're talking about here. We're talking about more dedicated to the fingerboard fingers. Okay? All right, hopefully you'll remember that. All right, terrific. Everybody happy? Good. Now you're going to be unhappy. No, I'm kidding. So yes, this next slide is challenging, but I'm going to try to run with an analogy that I think works pretty well. It is a really important slide though, because as we're talking about expertise, as we're talking about the expertise of someone like Steve Poe learning to be able to taste all these differences in wine and all that sort of stuff. The expertise of those sound engineers who can know how to reshape an environment so they kind of correct for the problems that would occur during TV and movie recording. Of course, the expertise of Daniel Kish, Brian Bushway, other folks we've talked about who have sensory deficits. All of that, the expertise, these kind of heightened perceptual skills are coming from plasticity, which is why it's important you understand a little bit about the plasticity story, okay? And it's important that you understand plasticity because remember one thing I talked about when we were talking about the blindfolding experiment? Somebody asked the question wonderfully, which I probably should have mentioned earlier, that yes, when you're done with your 5 days blindfolded, and you go home, those kind of changes in your brain, the fact that your visual brain area was helping with touch, that reverts back to the way it was before you had checked into the hospital and were blindfolded, okay? That is an example of short-term plasticity. And it happens, if you start to learn a skill, say you spend a week learning guitar and you say, this just isn't for me. When you did that for a week, there were changes, but not long-term changes. The long-term change, the long-term plasticity of your brain has to be facilitated by short-term plasticity kind of over and over again. Practice makes perfect by short-term plasticity becoming long-term plasticity. And that's true of any skill that you've ever mastered and what we're talking about in this class overall as perceptual expertise. Okay, so let's talk about this. What happens with short-term plasticity? Well, okay, here's where I'm going to use my analogy. And I think this works for people. It's, kind of imagine this. Probably most of you grew up in pretty modern looking apartments or houses. I used to live in the Northeast, and back there, things were pretty old. There were, certainly when I was a graduate student, I lived with a whole bunch of other guys, and we lived in a pretty old, rundown sort of apartment. It probably was a very pretty building at one point, but by the time we got there, it was as inexpensive as we could find. It was clear that it had been modified, so it probably, they changed a floor of a large family home to just a single apartment so they could, divide it up and have more people, more families living there and all that sort of thing. So you'd find things like, doors that really didn't go anywhere or had been painted shut. Okay, so in this apartment, okay, this old house apartment, we had a dining room table in, I guess, what you would call a dining room, and then there was a kitchen. But to get to the kitchen, what you had to do is you had to go out into a hallway and then go down the hall a little bit and then turn into the kitchen. I mean, the rooms were right next to each other, but you still had to go in the hallway. And that kind of became a pain, especially, when we wanted our friends to come over and we had to bring food back and forth. And then one of us noticed that there was a door between the two rooms. I remember thinking, oh my gosh, I can't believe we never noticed this. And the reason we never noticed it is because, first of all, we had our sofa in front of it. And secondly, it was painted the same color as the wall, and it was painted shut, right? And so we looked at it and we thought, wait a second, what's on the other side of this door? And we looked at it on the other side, and in fact, in the kitchen was the other side of the door, and it also was painted shut, and there was some sort of utility. I think maybe a rolling dishwasher was in front of it or something like that. We said, my gosh, we can use this door to go back and forth without going in the hallway, right? If we move the couch a little bit, if we move the dishwasher a little bit, and then open the door, then we can go back and forth much more easily and bring food back and forth, dishes back and forth more easily. So that's what we did. We kind of chiseled away the paint. You can imagine these guys in their mid-20s, kind of just doing all this crazy work on the house. And we realized, hey, you can open this door. This is great. The couch was still a little bit in front of the door. So you kind of had, when you go into the door, you had to kind of go sideways. But it did work. I mean, it allowed us to bring the dishes back and forth and the food back and forth pretty easily after a while. What we did is we kind of opened up a channel. We had opened up a connection that was there before. And when you first learn a skill, That's what's going on with your neurons. You're opening up connections that were there before but hadn't been working. What we say is these are dormant connections, right? And so these are connections, if you think of the rooms as neuron cells, and the connection being the doorway between them, by chiseling open that door and moving the couch and the dishwasher a little bit, we now started using what we would call a once dormant connection. And here we go. We're doing things better. We're able to move dishes and food back and forth better. Okay? That's kind of analogous to what happens with short-term plasticity. When you're first learning guitar, after a few days, yeah, you do become better at things, but you know that you got to keep it up, or what's going to happen? It's going to revert. Okay. Well, okay, this was working well for us, this door we chiseled. And what we decided to do is really clear away everything that was in front of the door so it would really work well. So we pushed the couch all the way to the side so it was no longer in front of the door. I think on the other side we had to move the dishwasher even a little bit more. And now this connection was working well. Okay. In other words, we made this connection as open as possible, as efficient as possible, so we could go back and forth easily. We no longer had to go into the hallway, and now that it was really opened, our connection was working well. Okay, our once dormant connection between the rooms was working really, really efficiently, and that's what happens as you learn more and more. The connections between these cells not only kind of reaffirm themselves, okay, they start working very efficiently. Okay, cool, that's great. And then we did something we probably shouldn't have done. It was working so well, and we are really enjoying we would leave the door open because it felt like the kitchen had more space and the dining room had more space. We were loving this. So what we did is the walls weren't very well made. We decided to get a sledgehammer and knock down part of the wall. I think one of us, I can't remember for certain, but I think one of us asked the landlord if that was okay. And the landlords had no interest in what we were doing. They didn't care. And so we knocked down part of the wall that was next to the door. And now, it's kind of like we had a little shelf there with all this opening. The door was open. We took the hinges, we took the door off the hinges, and now we had another open space there. And it really felt open. And now we didn't even need to go through the door anymore to pass dishes to each other and all that sort of thing. Things were working really efficiently. And that's what long-term plasticity is like. Not only have we reestablished the connection between these once dormant connections and made them more efficient by pushing away the couch, okay? We sustained that connection long enough so that we formed a new one, this case by knocking down part of the wall. And at that point, we had this really efficient, useful, and long-term solution to the problem. And that is the basis of long-term plasticity. That's why, if you're blindfolded for 5 days, it does revert because you've only gotten to the point of short-term plasticity. But if you lose your sight, it's going to induce long-term plasticity, and you'll be able to use your visual cortex for all touching forever. Okay, and it's not just those cases, those kind of very, extreme cases. If you're learning an instrument after you've practiced for a year, that could be your instrument potentially. If you've practiced, even when you're a kid, you'd be surprised if you went back to the instrument that you took seriously when you were a kid and you hadn't played in a long time. You'd pick it up pretty easily, and that's because that long-term plasticity. It has changed your brain and is maintained. Yeah, you'd have to familiarize yourself a little bit, but with kind of some of the rules of the instrument and stuff like that. But it's changed. It's like when you learn to ride a bike. At first, it's kind of takes practice and all that sort of stuff. But then, bam, you're on, and you've made your brain long-term plastic, and now your brain has changed in order to allow that coordinative act. And that's true of sports. It's true of any sort of behavior. It's true of perception too. That's what happens, for Stephen Poe as he's learning wine. It's got to kind of become second nature. It's like anything we've talked about this semester. Okay? It is the basis, importantly, of plasticity in the blind and all the perceptual expertise we've talked about and will talk about. So, okay, good. Hopefully the story of me knocking down a wall in an apartment I didn't own when I was a graduate student helps you remember that. But I want to give you another kind of a situation that was kind of an experimental, a lab situation that shows how short-term plasticity becomes long-term plasticity. And this one actually has to do with how the motor brain changes. And we haven't talked very much about the motor brain. Hey, where's my brain? Here it is. The motor brain now I'm going to talk about, it's a really perception course, but the motor brain is a little strip. The motor brain area is a little strip right in front of the sensory brain right here. Now I see the green screen's kind of messing this up, but it's just kind of the same shape, same size, but it's just shifted in front. Okay, so it has to do with learning a motor skill, but it equally applies to perceptual skill. But I think it's such a great intuitive example that it's going to be very useful for you. All right. So here's what happened. Subjects came into the laboratory and were asked to learn a keyboard pattern. A keyboard pattern on a, oh geez. Oh my gosh. Okay, sorry about that. My screensaver went on by accident. Okay, you probably continued to see this, but I couldn't. Here's a keyboard, like exactly like the type of keyboard that was used in the experiment. And they'd have people come in who didn't know how to play keyboard or anything like that and learn a keyboard pattern. I can't remember how long the pattern was. I think it was maybe a 20-note pattern. And they didn't hook it up to sound, although they did hook it up to a computer so they could kind of track how well people were learning the keyboard pattern. So maybe it was something like this. And they had to learn it and do it as smoothly as possible, so it wasn't just kind of having to learn the pattern, it was how to play it smoothly. And since these people had never done it before, it was tricky. They never played piano before. It took a lot of practice. But what they were interested in finding out is what happens to the brain as people practice. So what they did is this. It was in a laboratory. We could do this, I guess, now on our campus, right? We have an fMRI device, and we could absolutely try to replicate this if we wanted to. People came in, and they learned the keyboard pattern, and before they did, their brains were scanned. Okay, so ultimately what they're going to be doing is practicing 2 hours a day for 5 days. And what they're going to do is scan them before the 2-hour practice session and after the 2-hour practice session on each of those days, okay? And what they find is that people first go to the scanner before they start practicing, and they look to see how their motor area is organized. And at first, it's there's nothing special about it. But then they have them practice for 2 hours, and then they scan them again. And they show, yeah, in fact, the motor area, like the sensory area, kind of shifts around to kind of dedicate more room to those fingers. Cool, there's a little plasticity there. Okay, they go home and come back the next day. The next day, before they practice, they scan them, and they find, oh, their brains have reverted. Okay, that's fine. Their brains have reverted. But then they have them practice for 2 hours, and they scan again and say, oh, cool, okay, there goes the plasticity again. Now their brains look different now that they've practiced for 2 hours. That was this pattern across all 5 days. So on day 5, they come in, they get scanned, and they say, nope, it reverted again. Overnight, I guess it reverted. They practice for 2 hours, and then they show it comes back. Those are all instances of short-term plasticity. The brain reorganization only is appearing after the practice, okay? Cool. All right, that makes sense. That's short-term plasticity. Yes, it does change after 2 hours of practice, but it reverts. So when the next day they test it before the practice session, it's shown to be the same as it was before any practice at all, okay? That's short-term plasticity. All right. Then what they did is they said, okay, half of you now have to go home and practice some more, I'm afraid. And what those people had to do is practice 2 hours a day for 4 more weeks. All right, so you know what they're after here, but I hope they were paid well, or that's a lot of work. 4 weeks, 2 hours of practice a day. Maybe it wasn't every day, but it was almost every day. Maybe they gave them a day off because it would have been so exhausting, right? a day off a week, but you know, it was intensive practice. And then after that, they bring people back. They bring these people back, and they're going to have them show how well they've learned that pattern. And by 4 weeks, boy, they better know the pattern well, and they probably played it very smoothly. But before they do that, they just scan. I'm sorry, I'm hearing somebody's microphone, and so please check your microphones. I'm hearing somebody have a conversation. Anyway, those subjects then came into the lab before showing the practice, before going through the little 2-hour practice to show how well they had learned it. They get scanned.
And el perfume, how long did you in the with jams?
Please turn off your microphones. I don't know if anyone else can hear that. Please turn off your microphones. Okay. Anyway, what they find, and this is critical here, is they found for this group, that organization that was only observed after the practice sessions is now observed before the practice sessions. The brain organization appeared before the practice session, and it didn't make a difference if they scanned their brains after or the next day before a practice session or 5 days later before a practice session. Their brains were changed, and they were changed potentially forever. Okay, that is long-term plasticity. And so what I'm trying to do here is to give you a sense of, you know, how, again, practice makes perfect. And another way of saying that is short-term plasticity makes long-term plasticity. You know, by correlating how the brain is changing with practice, you all now have intuitions when you yourself have achieved long-term plasticity. Yes, so riding a bike is a great example of that. You've learned to ride a bike, and that was a situation where you went from short-term plasticity to long-term plasticity. You learned to hold a pen. You don't remember this, but holding a pen well enough so you didn't rip the paper or make inconsistent lines or stuff. That was something that you had to practice. But now, well, to the degree that you guys know how to hold pencils, you can do it based on your long-term plasticity learning. Any skill like that, including the things we've been discussing with these experts. J.C. Ho, the coffee expert, if you read about him in the book, exact same thing. He's learned to be able to distinguish coffees through smell. Certainly Stephen Poe. In their training, in their experience, their brain shifted from short-term plasticity, which would revert if not maintained, and then with maintenance became long-term plasticity. So that's why this slide, I know, is confusing. Hopefully my little apartment analogy helped a little bit, but it is in some ways the kind of core slide of the entire course. We're trying to find what's going on in the brain generally that's allowing this sort of perceptual expertise, these perceptual superpowers that we've been discussing all quarter. Okay, cool. Let me take a little break here, see if there's questions. And I know that's a lot on one slide. The story, Alexa says, the story sounds like it could be from a show like Friends. We look nothing like Friends, that's for sure. We were big time nerds. Are all plasticities doomed to be short-term due to old age? No, Paxton, that's a great question. In other words, do you lose these things? And I just saw an amazing example of this. You know, certainly as one ages, if in fact senility, and there's things that happen to the brain during senility that, yeah, potentially could make you lose a lot of long-term information. But I saw this beautiful example, and I'll see if I can find it. It's been making the rounds on the internet, of a woman who I think had very severe Alzheimer's, was not very communicative. And then I guess a grandchild or a child came in and started playing a piece of music that this elderly woman, this piece of music that the woman used to do ballet to when she was younger. And it's amazing. He plays the music, and all of a sudden she lights up and starts to go through these motions that you can tell were part of the routine. She's sitting and everything, but you can see her arms moving and her face is, kind of showing that she's completely involved in it. And it was like it tapped into this, kind of part of her brain that had been changed for the long term that she learned when she was younger, even though couldn't, she was not really communicative, her memory was not good and all that sort of thing. So there's still long-term plasticity there. It doesn't, depending on the type of senility, it might not hold for certain cognitive things, but it could very well hold for perceptual things and motoric things. And you find that with other things too. My son at one point was involved with something in his high school where he was trying to help senior citizens who had early senility, so they were still pretty functional, help facilitate their memories and their emotion through music. These are people who had played music most of their lives on an instrument of one type or another, and they would go to these homes and kind of try to get them to relearn these pieces if they had forgotten them, and it was just miraculous. I saw them perform; it was just wonderful. So. The movie, okay. Sabrina says, the movie Coco shows that when a grandson plays music for his grandmother, she remembers music from childhood. Yeah, music can be absolutely like that. That's a great example, Sabrina. Thank you. Okay, very cool. Oh, is some of this muscle memory? Yeah, so what's muscle memory? And I'm glad you asked this, Mason, because muscle memory isn't really muscles, right? I mean, it is muscles, but really interacting with the brain. So yes, when you learn something like a guitar solo or something like that, there's some solos I know on guitar that I could play even if I haven't played guitar for like 3 months or something like that. And you could say, oh, that must be muscle memory. Well, it's just an expression. Really, it is brain long-term plasticity that's controlling the fingers. So it does kind of come out, it kind of feels like it's muscles, but it's not. It's the brain, it's the nervous system that are controlling the muscles. It's a great question, thank you. Great, okay, then let's just do one more polling question, and then we'll finish up this discussion of plasticity next week. Okay. All right. So, oh, okay. Actually, this goes back to a previous slide as well. Is that right? Okay. I don't think you've had this one. Oh, did you have this one? I can't remember now. Yeah, you didn't have that one. Okay. Okay, you know this one, but it's a free question. Hey, it's a free question. Okay, this has to do with feeling for a key. So I reminded you of this, of course, in the beginning of the class. When would you be using your visual brain to help you touch? A, after 5 days of visual deprivation. B, after 3 hours of visual deprivation. C, when trying to identify a spatially complex object by touch, for example, a key in your pocket. Or D, all of the above. Too cinchy. Yeah, too easy. All right, I'll give you another 10 seconds, but you don't need it. So, great. Pretty much everyone got this right. I'll end the poll. The correct answer is in fact D, all of the above. And if you remember from that slide, yes, 5 days of visual deprivation, even without Braille training, which is really interesting, would induce your visual brain to help with touch. Even 3 hours of visual deprivation, it would enhance your touch sensitivity and also involve your visual brain, which is pretty amazing. So you don't need to, if you're really interested in doing this as your senior thesis or something like that, you don't need to put people in a hospital room for 5 days. You can do this in 3 hours, which is very, very cool. And of course, C, we talked about this. Yes, we all, even without visual deprivation of any major type, when we are feeling in our pockets for a key, without looking at the key, we will involve visual brain areas, at least to some degree. So the correct answer is all the above. Oh, I didn't share the results, did I? There you go. You can take a picture of it if you want to. Okay, that does it for today. Have a good weekend, everybody, and I will see you on Tuesday.
Bye, thank you, Professor.
Thank you.